In this class, we're going to consider complex conjugate pair solutions to quadratic equations. So that sounds a little complicated, so let's start by unpacking that, and then we're going to apply what we're going to learn to these two examples here. So if you take a quadratic equation, just a normal quadratic equation written in this general form here, we know that these guys can have up to two solutions. So either two solutions as a maximum, one solution, or no solutions. But that's all in the real number. So two real solutions, one real solution, or no real solutions. But the case where we've got no real solutions, we might have complex solutions. And now that we're working with complex numbers, we don't have to just stop at the point where we say there are no solutions. We can take that further and say, well, there are no real solutions, but there are solutions in the complex numbers. So just to kind of highlight that, let's change our x's to z's. So we're kind of making an assumption that we're working only with complex solutions. So we tend to use the letter z for complex numbers. So let's just imagine that we already know that we're going to get complex solutions and kind of updating our equation to make it look like this, okay? If you get two solutions, so this can still only have a maximum of two complex solutions. If you get those two solutions and they come out to be, let's say z equals alpha and then z equals beta, then that means that we can write our original equation in a factorized form. And the factorized form would look like z minus alpha and then z minus beta equals 0. Now, that might look a little complicated or unusual because we're maybe not used to visually seeing these different letters, especially these Greek letters. But basically that would just be the equivalent of, if you were working in the real numbers and you factorize, you might end up with something like x minus 2, x plus 5 equals 0. And then from that factorized form, you then get your two solutions. That's kind of what we're doing here. But what we're going to learn, so that's not really anything new or massively new, but what we're going to learn in this class, and the key takeaway, is that when you form your two solutions, alpha and beta, they're not just independent solutions, but they form what's called a complex conjugate pair. So remember that a complex conjugate of, well, let's say that alpha is the complex number a plus bi, then remember the complex conjugate, let's just call that beta, is a minus bi. So the same form, just changing the plus to a minus. Those are the conjugates, and these form what's called a complex conjugate pair. So when you take a quadratic equation and you've got complex, so non-real solutions, the solutions will form this complex conjugate pair, okay? If you're not too sure about the complex conjugate, then check out the class earlier in this series where we talk about that and some of the things you can do with it. But it's a fairly simple concept. It just means that if you've got a complex number in this form, then the conjugate is just changing that plus to a minus. So, or a minus to a plus, it depends which one you're starting with. So let's apply that to these scenarios here. So let's say we've got some quadratic equation and we know that one of the complex solutions, the complex roots, is alpha, which is the complex number 7 plus 2i. So if we want to find the second solution, we don't need to go through any kind of algebraic process. Well, we don't even know the equation, so we can't do that anyway. But what we do know, just by this complex conjugate pair idea, is that the other solution, the other root, has to be 7 minus 2i. So in other words, with these complex conjugate solutions, you only need to know one of them to know both of them, because you just apply the conjugate to get the other one. So it's a fairly straightforward idea, the fact that they always come in these pairs. They come in these pairs because of the quadratic formula. And we're going to look at that actually in the next class as some examples of how we kind of arrive at this. But at this point, we're just wanting to deal with the idea that these solutions to this equation come in pairs, complex conjugate pairs. What we could do though, we could now work our way back to the original equation based on these two roots. In the same way that if you were in the real number scenario, you could work back from this by expanding out the brackets to get back to the original equation. Now, you might wonder why we want to do that, and it's just a common question type really. That's the only reason, I guess, why we want to do it. But it throws up some quite interesting algebra, so let's just work our way through that. So we know that the original form of this equation should be z, sorry, that's a British way of saying it, z, if you're international, z or z, depending on where in the world you are. So let's call it z minus alpha, and then z minus beta. equals 0. That's a form of the original quadratic equation that we're looking for, but we know what alpha and beta are, so we can write this as z minus. Now, just be sure to use an internal bracket here, because this expression is, well, it's got two parts to it. So two terms. So z minus 7 plus 2i in a bracket. And then similarly for this one, z minus the beta, which also needs to be bracketed off. So 7 minus 2i equals 0. So what we want to do now is expand out these brackets. It's a little messy, but it neatens up fairly quickly. So we're going to do these guys, so z times z, to give us a z squared. And then we're going to do z times this bracket here. So that is going to be minus z times 7 minus 2i. Then we're going to do this guy times this guy, which will be minus z7 plus 2i. It's the fact that we're dealing with the conjugates, which later on is going to allow the algebra to tidy up quite quickly. And then finally, we've got these two guys multiplying. The minus times a minus gives you a plus. And then we're going to have 7 plus 2i times 7 minus 2i, and all of that equal to 0. Okay, so let's just start tidying this up a little. There is quite a few terms to deal with, but they'll tidy up quite quickly. So the z squared is going to stay where it is, and then we've got minus 7z here. You can, if you've done a few of these, start to learn the pattern, and you'll be able to jump a few, or maybe one or two lines of algebra, but initially just multiply out all the terms just so you know where you are. Minus z times minus 2i, that's going to be a plus 2zi. Minus z times 7 is minus 7z. Then we've got minus 2zi. These guys need to be multiplied out using FOIL, or whatever acronym you use for that. So 7 times 7, 49. We're going to get a minus 14i and a plus 14i, so they're going to cancel just by the fact that this is kind of in the form of like a difference of squares. And then we're going to have a minus 4i squared. So minus 4i squared generated from the final term. So if we look through this now, we'll see that those guys are going to cancel because they're the same term. These guys will give you, well, these guys will combine at least. So we're going to get a z squared minus 7 minus 7z is minus 14z. So they're taken care of. I squared, so remember that I is the square root of minus 1. So I squared is square root of minus 1 squared, which is just minus 1. So minus 4 times minus 1 is plus 4. So we're going to get 49 plus 4, which is 53. So plus 53 equals 0. And that's us gotten back to the original equation, like in this form here, that would give you these two solutions. So for this equation here, the two solutions are these guys, alpha and beta, this complex conjugate pair. Okay, so that just shows you how to basically work with these. Let's just have a quick look at the next guy. So let's say that we are told that this is the solution to a complex quadratic equation. So let's just maybe assign that to alpha. And just again to highlight the point that we already know that the second solution, the beta, has to be the complex conjugate pair. Well, they form a complex conjugate pair. It has to be the other member of that pair. So we just can go straight to writing 2 minus 3i without any work, without knowing anything about the equation. We could then work our way back like we did here. We're not going to quite do that, but just to set that up, we would then just do set z minus the first solution, the first root, which is 2 plus 3i. And then we've got z minus the second solution, the beta, which is minus 2 minus 3i. And then we would just work through the algebra again, just like we did here, picking up some of these patterns, some of these cancelling terms, and working it all the way back to a trinomial. So the main takeaway from this class, well, there's a couple of things. The first thing is that when you're working with a quadratic equation, you can either have two real solutions, or you can have one real solution, or you can have no real solutions. But now that we know about complex numbers, we don't have to discard the no real solutions and just stop at that point. We can still take those forward into the complex numbers and form complex solutions. When we do that, we get not independent solutions, alpha and beta, but we get a complex conjugate pair. Okay, and that is the main takeaway. If you know that complex conjugate pair, you can then work your way back, if you have to the original equation, Or in the next class, we're going to start with the original equation and just kind of work this backwards from the way we've done it here, from here going to the roots, to the solutions. It effectively works both ways. So hopefully that makes sense. If it does, then just to connect this to the opposite process, maybe just when you're ready, scoot on into the next class and check out the material there.